1, 2, 3. 1, 2, 3.
Yes.
There is some,
Yes.
yeah?
Yes.
Great, thanks. Are also algebraic varieties. And this was almost proved modulo some finiteness statement, for open covers of open subvarieties. And this is essentially a corollary of Hilbert basis theorem that we'll prove in a few minutes. But I also want to say that the last time we had an embedding like this, locally closed. But we could also have a quotient morphism like this. Okay, so sort of dual construction. And then there is some canonical topology on the quotient space. And also there is a notion of a regular function, namely a function here is regular if it's pulled back to x is regular. Okay, so there is a way to produce another ringed space, but then it's much harder to postulate some conditions when this quotient space will be again an algebraic variety. In contrast with this sub-variety case, this case of quotient variety is much harder. In a sense, it's the subject of the invariant theory that we discussed last year, for example. Okay, the only but very important example that will be in your home assignment is when this X is the punctured affine space, like this, and this Y is the quotient modulo dilations. In other words, just projective space PP and minus 1. Okay, and your whole home assignment will be about this example. So in this example, it is possible to equip this quotient space with the structure of algebraic variety, and this is the most important algebraic variety, projective space. And then just a bit of terminology. So a closed subvariety of the affine space is called what? Everybody knows. No, just a closed subvariety of n is called what? An affine variety, right? Okay, but for example, this thing is an open subvariety, and it's not an affine variety. By the way, why? Say if n is bigger than 1, why this complement, the punctured affine space, is not an affine algebraic variety?
Because we can look at the ring of...
Yeah, the global functions are the same as on not punctured affine space, and then by our main theorem, it should have been isomorphic to the non-punctured space, but it's not. Okay, so locally closed subvarieties of the affine space are called quasi-affine varieties. Okay, and similarly closed subvarieties of projective space are called projective varieties. And locally closed will be called quasi-projective varieties. Okay, so this is just a piece of terminology, nothing else. We will study them for the rest of our class. Yes?
How can we detect does the manifold, does the quotient space is algebraic variety? I mean, here it's automorphism without fixed point, without fixed points. In this situation, when we have an automorphism of finite order without fixed points, it's evidently that the quotient space is smooth. And that's why it's maybe algebraic variety. But if it is not smooth, what?
There are no smooth algebraic varieties, but once again, the question about quotients is very delicate question, and we will not discuss it at all, apart from this single example.
Because it's very primitive example.
Yes, that's true. Okay, so we will turn back to the Hilbert Nullstellensatz. We started another proof last time. Let's finish it. It will be a corollary of M-Noether lemma. Okay, so I have already formulated both statements last time. Let me at least recall the Hilbert Nullstellensatz statement. So it takes an algebra A, just the polynomial algebra in n variables, and it acts on a module M. This module M is finitely generated. Then in this algebra I have a linear form U. So this U is the sum of coordinates with some coefficients. And it's not zero. Then I claim that for any such a linear form, there is a polynomial, a monic polynomial Q E such that M modulo Q of U is not zero. Q of U M is not zero. And then the immediate corollary was, as we discussed last time, that this monic polynomial could be taken linear. Okay, maybe some constant C. Okay, and then I explained last time why this formulation is well, it's equivalent to the usual formulation of Hilbert Nullstellensatz as applied to modules which are quotients by ideals. Yeah, so the models with one generator. So now let's prove this theorem. And the proof proceeds by induction in n, in the number of variables. If there are no variables, then there is nothing to prove, so that's the base of our induction. If there is one variable, there is also essentially not much to prove. So we will consider more than one variable. Then we will need the following lemma. That is almost the same statement as in the theorem, but not for any linear form, but just for one. Okay, so there is a linear form, say V, in our algebra, and a polynomial, say R of t, such that M modulo R of V M is not zero. Okay, just a weak form of the theorem, not for any linear form, but for just one. And then,
What is V?
pardon me?
What is V?
V, some linear form. We can choose a linear form and a monic polynomial in it. Okay. Okay. So the proof of lemma. So it suffices to check for a non-zero quotient of M. Okay, and we'll choose sort of minimal such quotient, namely the one generated by a single element. Say M prime generated by a single element. So M is finally generated, and its quotient is also finally generated. But then, if it's generated by three elements, let's kill one of them, then another one, and we're left with the singly generated module. But then, if it's generated by one element, then it's isomorphic to the quotient of our ring itself by some ideal, right? So M prime is isomorphic to A modulo some ideal J. Okay. Now, if J equals 0, then there is nothing to prove. Yeah, I think everybody agrees. I mean, just take any coordinate and you are done. Okay. Now, if J is not 0, then it contains some element, some non-zero element F. Okay, and now we can start using M-Noether lemma. I mean, we will choose a coordinate system good for this function F. So we can find by Noether lemma, find a coordinate system y1 and so on yn, such that F is monic in the last variable yn. Okay. Now, if n equals 1, then again there is nothing to prove. Yeah, and we can take r equals what? So we wanna. So our linear form essentially. There is just one variable, so our linear form is this variable, y. Yeah. What is the polynomial we wanna? The polynomial r we wanna take in this case. Come on.
X to x.
No, not quite. I would take R equals F. Yeah, because F kills our module, and hence this quotient is not 0. Yeah. The module is not 0, but this is killed by our. Yeah. Fine. So if if n is bigger than 1, then we can consider A over F, right? And since F was monic in the last variable, it means that this quotient is finally generated over all the rest variables, right? Is finally generated over, say, B equals polynomial algebra in y1 and so on, yn. Oh, sorry, yn minus 1. Okay, just because f is monic in the extra variable yn. That's fine. That's good because we have this algebra A over F, and it surjects onto A modulo the whole ideal J, right? F was an element in this J, in our ideal. And so this is finally generated over B, and hence this is also finally generated over B. Okay, but now B has the smaller number of variables, n minus 1. So our induction assumption is applicable to B, right? By the induction assumption for n minus 1. We can take, say, U, yeah, because our theorem is already established for n minus 1 equals V equals y1, for example. And then for this U, this theorem asserts the existence of polynomial Q, yeah? And this will be our polynomial R. Okay, so we proved something. We proved this lemma, a weak form of our theorem, right? By induction in N. Now we want to deduce the strong form of our theorem for any N. Okay. So it remains to deduce the theorem from lemma from its weak form. Okay, so pardon?
We just can take U by induction.
No, the theorem asserts that this holds for arbitrary U, for any U.
No, we speak about lemma.
Yes.
That we prove our
yes.
lemma.
Yes. We have finished the proof of lemma.
Yes. Okay. We deduce from the fact that a quotient by F is finitely generated.
Yes.
And thus generated our B. And for B, we know that there is some RT such that blah blah blah.
No. For B, because it has smaller number of generators, we know the strong form. We know the theorem by induction.
We know what No, no.
No. We are proving our theorem by induction in n. And we already proved it for n up to 10.
I understand.
And then we can deduce this weak form, lemma, for n equal to 11. So when we know the theorem for n up to 10, we can deduce this weak form for n equals 11. Right? And now we proceed with the proof of our theorem for n equals 11.
Sorry, I don't understand. We have proved
It's just-
lemma, isn't it?
Yes, we proved lemma for n, assuming our theorem for n minus 1.
Yes.
Fine. Now we're proving theorem for n.
Okay.
Okay, so let's deduce. So we know that m modulo r of v m is not 0, and want to prove something for u acting on this m. But again, it suffices to prove for any quotient. For example, for this one. To prove the theorem for any quotient of m, namely m modulo r of v m. So we may assume that r of v m equals 0. Okay, so we replace m by this quotient, and then we assume that r of v m is 0. Okay, but now we are given some other linear form u. We know this for v, and we want to prove this for u. So two cases. First, if u is proportional to v, then what do we do? Yeah, so we have to do nothing. Then up to rescaling q equals r. Fine, we have nothing to do. Second case, that u is not proportional to v, but then we can use them to construct a coordinate system. Yeah, they are two independent coordinates. So then there is a coordinate system such that, say coordinate system z1 and so on, zn, such that, say, v equals zn, and u, say, equals z1, and n is bigger than 1 automatically. Okay? And then we know that r of zn, m, is 0. But then it means that m is a finitely generated module over the smaller algebra B in the other variables up to zn minus 1. Okay? But this is our induction assumption. Then we apply it to this situation. Just because we replaced our model by its quotient. So if we know that this claim is true for a quotient of m, then it's a fortiori is true for m itself. Okay, so M is finally generated model over the smaller algebra, and we are done by the induction assumption. Okay, so that's it. The theorem is proved, and this proof is due to, well, to Joseph Bernstein, and I know it from him just because I was his student. He is a teacher of mine. And what else can I say is he is still working in Israel, and he is also a mathematician of Jewish origin as well as a minnoiter. So I think that this other proof makes for this dirty trick proof was due to other three mathematicians of Jewish origin. So this is an honest proof that used nothing, no axiom of choice, no Zorn lemma, no dirty tricks, just an honest and rather short proof. Okay. But what it does use, it uses the notion of module somehow in the original Hilbert proof, and this dirty trick proof there were no modules, yeah, just ideals. And here we essentially used modules. Okay, so now along the same lines, now let's prove the Hilbert basis theorem. And again, well, its original formulation was about ideals, but in reality, it says something about modules. So, what does it say? That it says that over A, our polynomial algebra, any submodule over a finitely generated module M is also finitely generated. Okay, and this property is called Noetherian property. Say of M, because this is a property of M. But then since it's true for any finitely generated model over this ring, then it's also a Noetherian property of A. Okay, and in particular, it has an immediate corollary that any ideal J in A itself is finitely generated. Yeah, just because we apply this claim to the free rank 1 module A, and then by definition any submodule of a free rank 1 module is called ideal. Yeah, but well, this is well known, I hope. Fine, but in fact it is equivalent to the statement because any finitely generated module is finitely generated because we have a surjection A to some power to this module M, and if we have some module M prime, then we can take its pre-image here, well, let's call it M prime tilde, but then it will be, well, it will be reduced to the sum of ideals. So maybe there's an exercise, but it's a very straightforward exercise. That is essentially these two formulations are immediately equivalent. Okay, so let's.
Sorry.
Yes.
What theorem states?
Pardon me?
The last theorem. What state?
This is the Hilbert-based theorem.
The last.
This is the theorem. Yes.
I didn't see.
Yeah. So if you can prove this claim about ideals in the algebra, then we can prove this.
Sorry.
Which square?
Cartesian square. Cartesian square. What is the
That's sort of hint how to prove this. We want to prove that any submodule of M is finally generated, but you cover your M with a free module, and then you consider its pre-image, and this will also. It suffices to prove that this one is finally generated because this is a quotient. But then it's easy to deduce this from ideals. Okay, so let's prove this. So let's take an ideal again, J in A, and if it is 0, then we are done, just as before. And if it's not 0, then there is a non-zero element. And we can consider the quotient J modulo the ideal generated by F, and it is a submodule of A modulo the ideal generated by F. Okay. Now apply the lemma of M-Noether. But by the way, this Noetherian property is certainly after M-Noether. The name is after M-Noether, just for this reason. So by her lemma, F is yn to the power d plus something. So A modulo F is finitely generated over over B, that is the polynomial ring in the smaller number of variables. Okay, and we can use again the induction in the number of variables. In N. We already know this statement for the smaller number of variables, so any submodule of this is finitely generated. So in particular, J modulo F is finitely generated. So A modulo F is finitely generated over B, and hence J modulo F inside A modulo F is also finitely generated over B, and say by induction. By induction in N, we may assume this. So say F1 maybe bar F capital N bar are some generators. So I mean f I modulo f equals f I bar. Okay. So then those lifts f1 and so on, f capital N, and now f itself generate J, our ideal J. And that's the end of the proof. Okay, so very similar argument. Yes.
Нижний диаграмм эквивалентна этой теореме, да?
No. This diagram should be erased and forgotten. It was just to hint how to deduce the theorem from this corollary. So
Теорема эквивалентна следствию.
absolutely, yes. So the corollary is formally just a part of the theorem when you apply it just to submodels over the free rank 1 module. But in turn, the theorem can be deduced from this corollary by such consideration. But let me maybe erase something to forget about it.
Как вы заключили, что J фактор по F конечно порожден? Потому что...
Because it's a submodule over of this, right?
Так, но это же не означает.
So this is a finally generated module because of this monic property. Yeah, the f was monic in the last variable.
Да, но отсюда не следует.
So this is a finally generated module over B, right? But B has n-1 generators, and so we can apply induction assumption to it. We're proving the theorem by induction. We want to prove it for n variables, but know it for n-1 variables. Just as before. So it's a very similar argument to what we had before. Okay. And now we can prove what remained about locally closed subvarieties. Namely, we wanted to prove that any open subvariety in the any open subset in an affine variety was quasi-compact. Yeah, so it could be covered by finitely many basic open sets, right? So our debt from the last time was that any open subset of an affine algebraic variety could be covered by finitely many basic open subsets DFI.
Мы скажем, мы докажем, что конечное число. Мы не доказываем, что конечное число.
But that's exactly what we need to prove, right? So that was our debt, and now I'm going to prove this right away. So we know that this open subset U in X is the union of the base open subsets D Fi, but this is a priori an infinite union, and we want to find finitely many. So let's consider the complement. Say Z, that is X without U, is closed. And by definition of the Zariski topology, this is the zero set of some ideal. Of some ideal J. But now this J is necessarily finitely generated. Okay, but by the Hilbert basis theorem. Okay, do I need to argue about this? I mean, we proved the Hilbert basis theorem for polynomials, but I am using it for arbitrary algebra. Maybe like this. But anyway, this is a finitely generated algebra, so it's covered by the polynomial algebra. And in here we have some ideal J, but again, its preimage is some ideal J tilde in here. And this is finitely generated, and hence its image is also finitely generated. Okay, so the Hilbert basis theorem works not only for polynomial algebras, but for arbitrarily finitely generated algebras. Right? Okay, and that's it. I mean, those basic open subsets will cover our U. Well, D F1, no, D F capital N. Well, once again, this J tilde, the full preimage, is an ideal in the polynomial algebra, and we know that it's finitely generated. So it has some generators, F1 and so on, F capital N. There are images in J will generate the ideal J by definition. There is a surjection like this, so anything is generated by. Okay, fine. So I don't know. Maybe let me write this down, just in case. Right here, that the same is true for any finitely generated commutative algebra. Sorry, script A. Okay. Fine. So now let's study some more of Zariski topology. And on the one hand, this is a rather lame topology, yeah? As we discussed, say in dimension 1, all the curves in Zariski topology are homeomorphic. Yeah, because the topology is just the closed subsets are finite subsets. On the other hand, in some respects, this comes in quite handy. So let me formulate some basic properties of Zariski topology that will be rather pleasant. Well. say the first definition is that if any open subset U in X is quasi-compact, then X is called Noetherian. So we have just proved that the affine algebraic varieties are Noetherian. And from this it follows that any algebraic variety at all is Noetherian, right? Because it is finitely covered by affine algebraic varieties. Varieties are Noetherian. Okay.
So we deduce that if A is Noetherian, then spec A is also Noetherian.
Right. We have just proved it.
For all Noetherian A.
Yes, but
not necessarily infinitely generated by.
no, all our, well, by default, all our algebras always are unital, commutative, finitely generated, and mostly without nilpotence. Okay, so this assumed, this tacitly assumed always, yeah. Fine. So now let me reformulate it, sort of lemma. That X is Noetherian. Pardon me? Yes, yes. But the topological space underlying affine or any algebraic varieties, they have this Noetherian property. So X is Noetherian if and only if any descending chain of closed subvarieties or equivalently ascending chain of open subvarieties eventually stabilizes.
What is X?
Pardon me?
What is X? Topological space for...
Yes.
What is
Yes.
the subvariety of a topological space in this case?
No, I understand. There is a definition. A topological space X is called Noetherian if any open subset is quasi-compact.
But in lemma you are writing X and then using subvarieties.
Ah, closed subset. Sorry. 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 Okay. So how to prove this?
Это точно правда, да?
I hope so.
Ну, сам почему-то. Написать как расчетная база, что-то такое.
I hope not.
Мы сейчас...
Means that any open cover has a finite open subcover.
Покрытие обязательно сейчас.
I think not necessary. Really? Okay, sorry.
должна быть эквивалентна в этом случае. Наверное, нужно предположить счетную базу в точке или счетную базу вообще. Давайте напишем, что x имеет счетную базу, и все будет хорошо.
Можно доказать, попробовать.
But maybe.
Можно проверить. Может, конечно, да.
Or maybe quasi-compact means for any countable cover there is a finite subcover. Maybe this.
Нужно направо, если мы...
Просто у нас вообще была цепочка, нам нужно эти блочки.
Okay, so how do we argue? Say let's consider such a chain. X, x1, x2, and so on. X, and so there are closed subvarieties. Closed subsets, sorry. Okay, and then there is their intersection. Maybe let me call it Z, sorry. Z, and then Z is the intersection of all those ZI's. And it's also closed, so U is the complement, X without Z. Okay, and now we can consider, say, UI is XI, sorry, ZI intersected with U, and this will be again a descending chain of closed subsets of U, and its intersection will be already empty, right? So U1 inside U2, so on, and the intersection of all those UIs will be empty. So this means that U is the union of their complements.
Why is the intersection empty?
Just by definition. Okay. But then we can choose a finite subcover from this, and we are done. Okay, and conversely, how do we argue? Any suggestions?
If we have an open cover, we can consider union, so first element, first two elements, three elements.
Yeah, just let me maybe say that there is a finite subcover capital N, and hence Z capital N plus 1 is already empty. Oh no, sorry. What did I say? Z capital N plus 1 equals Z N. So Z. Okay. So how about converse?
We can consider any cover, and
Yeah.
I think having it to be countable.
Okay. Yes. So let's assume this countable quasi-compactness.
Your chains are finite or
No. Huh?
are your chains like countable?
The chains are countable. Yeah. The chains are countable.
One can also consider non-countable chains.
This I don't know. Yes.
Вот это вот условие, оно не обязательно про countable chains, то есть там Там типа
And what is an uncountable chain?
ну типа
I
для
just don't
любого
know.
чума,
Это
там,
принцип
что-то такое.
сам linear order set.
Okay, but maybe let's not go into this. Okay, yeah,
Ну, там, наверное, через теорему замена, да.
yeah. But still, how do we argue in the opposite direction? Conversible. Uncountable case, yes.
And open color, and then take a chain like first element of this color union of first two elements of this color, etc. And it will be ascending chain of opens. So it's stabilized and
Yeah, okay. So U1 in U1 union U2 in U1 union U2 union U3 eventually stabilizes. And hence the whole thing U is the union of UIs. Okay, fine. So now let's consider the notion of irreducible components. And the idea is like this. So this is an algebraic variety given by, say, equation xy equals 0 inside the affine plane, sort of coordinate cross. Maybe I should draw it like this. And it is connected, as you see, but not irreducible. Yeah, it has two irreducible components, the two lines, and we want to somehow axiomatize this situation. So we say that X, that again, topological space X is irreducible if when X is the union of two closed subsets, then necessarily X equals Z1 or X equals Z2. This is the definition, yes. And in our usual real topology, this almost never happens. Yeah, I mean, on the one hand, certainly we'll imagine an interval as being irreducible. On the other hand, it's a union of smaller intervals like this and like that. And in this definition, it's not reducible. Okay, so this definition only makes sense for very coarse topologies like Zariski topology. Okay, so for the usual real fine topology, it makes no sense. Okay. And also the usual real varieties or topological subspaces of the real line, they are never, almost never Noetherian. Yeah, only if they have finitely many points, something like this. So this definition makes sense for Noetherian topological spaces. No, you may, but you get nothing interesting. I mean, for real line, the only irreducible subsets will be just points, nothing else. So it's an empty subject. But for algebraic varieties, it makes sense. And say lemma that in a fine algebraic variety is irreducible if and only if A is integral. That means has no zero divisors. Okay, let's prove it. So we know that the closed subsets in Zariski topology are given by ideals. Yeah, so X is the union of Z1 and Z2. Say Zi and Zj. What does it mean for the two ideals? That the whole thing is the union of those things. So these are zeros of ideal I, these are zeros of ideal J. So at any point, at any point, either a function from I vanishes or a function from J vanishes. What does it say about the ideals I and J? No, not quite, but rather warm. Right, absolutely, yes. It means that I dot J equals 0. But we exactly assumed that, say, in one direction, we assume that our ring is integral. So there are no zero divisors. So this can only happen if one of them is 0. Okay, and that's exactly our condition. And conversely, so suppose our ring does have 0 divisors. Say A times B is 0. Then what will be our A?
We can make the same group.
So what will be Z1?
ZA.
ZA, yeah. And Z2 will be ZB, yeah. Fine. Okay. So the next lemma is that any Noetherian topological space is a finite union of its irreducible components. Maybe I should say what is an irreducible component. Yeah. So an irreducible component Z of X is a maximal irreducible closed subset. Yeah, so for example, any point here will be a closed subset, but it's not a component. But say the vertical line is a component and the horizontal line is a component, and there are just two. And lemma says that in general there are only finitely many irreducible components. Any Noetherian topological space X is union of finitely many irreducible components. So, how do we prove this?
Либо x само,
Right, absolutely. So we start with what happens. X can be irreducible by itself. Then we are done. So if X is not irreducible, then X equals, say, X1 union X2, two components. No, it's not necessarily components, but they are closed. And if they are both irreducible, then again we are done. Otherwise, say, suppose that X1, but, well, so what are we struggling with? With the possibility to have infinitely many components. Now, if both X1 and X2 have finitely many components, we're done. So one of them must have infinitely many components. So say if X1 has infinitely many components, right. Then X1 is, or maybe let's say X2. Then X2 is X3 union X4, and they are simultaneously components in X, and so on. And it means that we have the infinite descending chain of closed subspaces, right? X2, and this contains, say, X4, and this contains X6, and so on, is an infinite descending chain of closed subspaces. Okay, but we assumed that it was an Noetherian topological space. Okay. What else do I want to say? Again, what does it mean? What does it mean for affine algebraic varieties? So if X is the spectrum of A, affine algebraic variety, then the irreducible components of X are, well, let's see, X equals X1 and so on, X capital N, and the Xi is also an affine algebraic variety because it's closed in X. So who are those rings AI? How do we see them algebraically?
Факторы по простым идеалам.
Right, absolutely. So AI is A modulo PI, prime ideal. Because it's a sort of tautology, yeah? Because AI is a quotient algebra of A, and AI has no zero divisors. Hence, the kernel of projection from A to AI is a prime ideal. It's just a definition of prime ideal. But
say that Xi is all ideals that contains some prime ideal.
I don't understand. Who these or who? I don't understand. Xi is a closed subvariety of spectrum. So what?
But
How can we detect our row I?
PPI. Yeah, that's my question. So who are those PIs?
no. Xi is Xi a subset of X?
Oh yes, certainly. These are irreducible components. So they are maximal irreducible closed subsets.
But it's a spectrum of closed string. Is it?
Because by definition, any closed subvariety is the spectrum of a quotient algebra, right? That's the Zariski topology. All the closed subvarieties are by our big theorem, they are spectra of quotient algebras.
Maybe I don't.
So the question is, I didn't even finish formulating the lemma. Who are those?
I don't remember, but I think that our PI should be minimal prime ideal.
Minimal prime ideals. Yes. Again, it's sort of tautology, yeah, because we have this big theorem about anti-equivalence between spectra and algebras. So if these are maximal, then the corresponding ideals should be minimal. Yeah.
If our prime ideal minimal, then spec is bigger.
Yes. So the PIs are the minimal prime ideals of A. Okay. So, well, somehow this speaks for itself. And there were, maybe just let me say in this case, when A was K of xy modulo the product xy, then what is P1?
X and
Yeah. And P2 is y. Okay. So I think that's it for today. Thank you. And I'm sorry, the second part was essentially void of content, but just mostly terminology. But the next time maybe we'll have some more sensible class.